Okay. Yes, let's move on to the final stage. Let's begin with the opponent challenging the problem.
没有，讨论的时间就算在里面了。
So we want to challenge the problem 5, ping pong racket.
We accept.
Great. Begin with the preparation part.
afternoon, fellow contestants and honorable judges. I'm Michael from Team MD Bridge, and today I'm going to be reporting problem number 5, ping pong rocket. This is our outline. And the problem statement is, the ping pong ball is placed in a container of water. When the container is dropped, the ping pong ball will get launched to a great height. What maximum height can reach with up to 2 liters of water? And our main focus will be investigating the relevant parameters and maximizing the rebound height. And this is our demonstration video on the left, on the right. Okay, so on the left, you can see that when the container drops to the ground, the ball sinks inside the water. And this is our experiment setup. We use a high-speed camera to record the process, and we use the electromagnet for our setup. And now into the assumptions and prerequisites. First, the containers and floor do not deform throughout the experiment. And we assume that all the energy upon collision transfer into the collapse of the crater. And third, we neglect the effect of dynamic viscosity because it causes very minimal error to our data. And now I'm going to talk about the theory. First is the falling phase. The force equals the gravitational force, the inertia, and surface tension force and resistance force. And the gravitational force and inertial force cancels out, so it equals to 0. So there will be only surface tension and resistance force acting during the falling phase. And we observe that the surface tends to be like an hemisphere during free fall. And here we don't consider buoyant force because during free fall is under a weightless condition, which there is no buoyant force. And now we're talking about the collapse of the crater, the collision phase. Now, the mass of the cup fluid system times the vertical acceleration equals the mass of the cup fluid system times gravitational force minus the air drag force. And the equation down below is energy equals the mass of breaking water, which is the part of water between the section of water between the 2 red lines. And the uppercase G is the acceleration of the system after collision. And the energy divided by the volume will be rho and uppercase G times h, and equals rho and v divided by 2. And delta rho is the fluid density, and the volume, the v is the volume of breaking water. And the energy transformation is, it starts from potential energy and transfers into surface energy, and at last into the kinetic energy of the ball. Now moving on to the calculation of jet height. The uppercase h is the jet height, and it equals u to the power of 2 divided by 2g, and equals the accumulation coefficient when we transfer it into v to the power of 2 divided by 2 gravitational considerations, and v equals the coefficient times delta h, and the uppercase g divided by the gravitational force. And because the uppercase g and divided by the gravitational force is equal to the initial height divided by delta h, so we can get that the jet height is equal to the coefficient times the initial height. It's proportional. Okay, thanks. Now talking about energy transfer from the jet to the ball. Here we break it into 3 aspects. One is the law of energy conservation, the change of momentum, and mass conservation. And P is the force that is acting on the ping pong ball. And it can also be written in this version. When rho is the fluid density and R0 is the jet radius. uppercase edge is the maximum jet height without the ping pong ball, and the lowercase edge is the height of the jet. And the velocity is the velocity of the ball. And here the acceleration is force P divided by M, which is the acceleration of the ball minus the gravitational force and the air drag acceleration. And the velocity causes the acceleration times delta t, and so we can get this equation. Next. And the boundaries of the model are the initial height limitation, which is from 30 centimeters to 170 centimeters. Here we can't do it, and we can't keep doing it when it's above 170 centimeters because the container breaks, and you can't do it below 30 centimeters because the ball hits the bottom of the container, which doesn't actually match up to your model. Now moving on to experiment 1. Our independent variable is the initial height, meters of 20 centimeters. Control variable is the container and the amount of water, which we use 100 milliliters. And the maximum, and this is the graph of the maximum jet height. And here, the part on the left, the crater isn't completely formed, and the one on the right, the crater is completely formed. And we could judge that by looking at the contact angle of the water and the wall of the container. And from this data shows a linear trend after the crater is formed. And we can get that the coefficient is 1.55, which we use the linear optimal method. Going on to experiment 2. Our independent variable is the initial height, and it is 20 centimeters. The control variable is the container amount of water. And the dependent variable is the rebound height. And through this graph you can see the initial height and corresponding to the rebound height. And it shows an exponential correlation, which I think is because of air resistance and the maximum fraction of energy that's transferred from the jet to the ball. And experiment 3, independent variable. The radius of cups, different cross-section areas here. The control variable is the depth of the water and the initial height. And we found out that the best effect is 4.5 centimeters. And it generally shows a negative correlation, but because the bigger the cross-sectional area is, the bigger the water surface is, which causes more energy consumption. But noticing that there's data that doesn't follow this trend because the smaller because the radius will be too small, and because of pressure difference, the ball moves towards the wall, which also results in energy consumption. And we're on to experiment 4. We have the independent variable is the amount of water, and control variable is the container and initial height, which is 150 centimeters here. And here's our data. This is the rebound height corresponding to water volume, milliliters. And it also shows an exponential trend because I think that different depths of craters are formed due to different volumes of water when it's dropped. And we're referring to the theory that I said before. The theory explains that the more volume of water I use, there will be a longer distance of the delta H. Okay. And as a rebound height to the initial height is the overall data, and the different colors represent the different amount of waters here. And the greatest rebound height we get here is under the condition 200 centimeters and 100 millimeters of water, and it is 660 centimeters of rebound height. Okay, now in our conclusion, the amount of water, the radius of the container, and the initial height are the three main factors of this experiment. And although the maximum height shows a linear trend, the rebound height doesn't show the same trend, because I think that air resistance and maximum fraction of energy will be impacting the result. So it wouldn't be the same. And within the boundary limitations, the amount of water and the rebound height are positively correlated, like according to our graph, our data. And in our experiment, the greatest rebound height is investigated, which is approximately 660 centimeters with the condition 200 milliliters of water and 170 centimeters of initial height. And this is the end of my presentation. Thank you.
So I'm the opponent today. First, I want to ask if you try to control the position of the ping pong ball at the center of the container.
Yes, we.
Okay, I got it. So, in yourself, could you explain more about how do you try to control the angle between the ground and the container? Do you try to control it, or you haven't do it?
Oh, we didn't control, but we.
Okay, I got it. So, in your slide, you say that you try to change the amount of water, right? But the problem statement say that you have to, you can use up to 2 liters of water. So you only use the water from 100 mole to 300 mole, right?
Yes.
Okay, I got it. So what do you consider is the main force to cause this phenomenon process?
Capillary force.
Okay, I got it. So, do you change the ping pong ball? Just because I consider that the surface tension of different ping pong ball would be affected. I mean,
We didn't do it.
so you always use the same ping pong ball?
Yes.
Okay, I got it. So could you turn to page 10? Okay. So in your slide, you consider that the initial height will be higher and the bounce height will be higher, right?
Yes.
Okay, I got it. I will discuss later. So which will affect you more? You mean that the contact area or the contact angles? Just because I want to know that if the contact area and the contact angle with the ping pong ball and the surface of water, do you consider it will affect or which will affect more?
Pardon?
The contact area between the ping pong ball and the surface of water would affect. So I consider that there will be some buoyancy. Okay, I will discuss later. It's okay. So in your slide, you consider like you ignore the buoyant force, right?
Yes.
Okay, I will discuss later. And okay, that's my third question.
give you a stabilization speed.
So I'm the opponent today from Team Skyber. So I'm gonna challenge the current fight, the ping pong ball. So when a ping pong ball is placed in a container of water, when the container is dropped, the ping pong ball will get launched to a great height. So the reporter has to investigate if the maximum height they can reach up to 2 liters of water. And for a summary of a report, I consider the theory, they have considered the falling phase and collision phase, and assume that the energy is completely transformed, and they also assumption that the container is not broken, and there is projectile motion and the surface tension. And they also use the fluid density and calculate the maximum jet height. But the report say that it will ignore the buoyant force. But I will discuss later because I consider there will still be some problem. And for experiment, they try to use the different parameter, like they use different volume of water. But I consider the problem statement say that it's up to 2 liters of water. So they only use 100 to 300. I consider that this will have some problem, so I will discuss later. And for initial height, so because the assumption of the reporter is that they consider the container will not break. So they consider when the initial height is higher, the bounce height will be higher. But I consider it would be some problem. And a radius of a cylinder, a radius of a container. And for cell, they use high speed camera to observe, and they use tool to drop the container. And the result is a boundary condition with a 30 and less than jet height and less than 100. And for reporter, according to strength, he has done some quantitative phenomena explanation and some simple fixed explanation for this physics process. And for suggestion, I consider he lack of some quantitative comparison between the theory and experiment. So because I didn't know that how the theory line they get, so I will ask them more clearly later. They need to explain more about the energy losses because they just assume that the container didn't break yet, and they should consider the surface area effect. Just because I will ask the reporter to explain later, and they didn't control the contact angle between the floor and the container because I consider that and when they drop the container, it should be perpendicularly dropped to the ground. But in themselves, they didn't control the contact angle between the container and the ground. And the volume of water should be more, up to 2 liters of water. So the discussion later. So I will ask the reporter about some suggestions about the control of angle contact to the ground and the amount of water and for mechanism. So I consider in this problem is the main fixing process behind the jet and how it caused to this phenomenon. And for the method, I want to know that how to actually transfer during the process and potential and kinetic energy, and about the force, how it affects the water container in the boat, and the data analysis. So I consider the reporter have to compare the theory and experiment result and the limit height of the ping pong ball. So thanks. So I will go to the blackboard. Let's move to blackboard. So in my opinion, I consider it will be look like this. This is a container, and it's a surface of water, and then will be the ping pong ball. So how would you consider the force affect the ping pong ball? Could you show me the force affected on the ball? Maybe like a gravitational force or the surface force, surface tension force. You can use the
falling or
so when the ping pong ball is contact to the surface of the water. So could you show me the force that would act on the ball? I mean, so in your explanation, okay, you can draw it.
maybe when it hits the floor or when it's in the wrist phase when it's falling.
Okay, so like I said, the container is hitting the ground. Okay, and the ping pong ball would contact the surface of water. So could you show me the force acting on the ping pong ball here right now in this moment? Could you just directly draw the force? I mean, yes. So like in your slide, you try to calculate the force acting on the ball, right?
Yeah, so the kinetic energy
What do you mean the kinetic? I mean the force, not the energy active. Okay. So let me ask another question. Do you consider that there will be the buoyant force because you say that ignore? Okay. So because you say that you ignore the buoyant force, but like the physics class you may learn, when you put a ball into the water, but if the buoyant force is more than the gravitational force, it would cause it to bounce. So why do you consider that you can ignore the effect on the buoyant force?
I mean, it's really falling because
Yes.
it's under a weightless condition. That means no gravity acting on it. And if there's no gravity, there wouldn't be buoyant force.
Okay.
Yeah.
So, but in your slide, I didn't really understand what the jet means. Could you explain the physics process behind this phenomenon? The jet means.
And the water is affected by capillary force, and upon collision,
So,
the water resilience, because of the water resilience, it comes back to surface and therefore forms a jet that pushes the ball.
okay. So because the container is hit the ground, so do the ground would give some pressure or some weight to cause the water giving force? Because the container hit the ground, right?
Yes.
So do you consider that the ground will give you a force? I mean,
Yes.
Yes. So do you consider it will affect?
Yes.
Okay. So from a perspective, I consider this phenomenon which is affected by the pressure, the acoustic wave that affects by the ground. It will give you the waves to the water and the ball. So do you agree with me, or you can explore about your jet? Okay. So let's talk about your slide. So you just turn to page 9. Yeah. So could you explain what the G means? I didn't really understand in your slide.
Oh, the acceleration of the whole system
Do you repeat
when it
again?
upon collision. Oh, the acceleration of the whole system upon collision when it hits the ground.
Okay, so you can
There's an
so
acceleration.
do you consider that G is a constant, or it will be affected by different experiments?
It will be affected by.
Okay,
Many
so
factors.
so do you try to measure or determine what the G will be look like? So because like you want to know maybe the volume or the velocity by this equation, right? Okay. So could you turn to the page 12? Yes. So because the equation will be very complex, so I don't really understand what the P would mean.
The whole force that's acting on a bubble upon collision.
Okay. So you consider that also the density fluid density will also affect the pressure or the P, right? So let me okay. So because you say that you ignore the viscosity of the water, so could you explain more about why there's still fluid density? I didn't really understand it. Just because, I mean the meaning of this, the fixed meaning. I mean why they still have to consider the fluid density. That's okay. Let's come to the next question. Could you turn to page 70? So in this graph, I consider that it's not exponential because I consider the exponential will be like this. I mean the exponential will be.
There you go. This trend could also be an exponential trend.
Okay. So you consider that there will still be a boundary condition on the rebound height, right? I mean, so you think that there will be a limit and a condition that would cause the rebound height difference. I mean just because. Okay. So in your previous slide, you say that the initial height is higher, it will cause the more rebound height.
Yeah.
It is linear, right? Like the big H equals to K times H.
Yeah.
Okay. But in this graph, I didn't think that it's linear, and it seems like
This is the rebound height. This one is the rebound height.
yes.
And the one linear is the maximum trend height.
Could you explain more about the maximum height and the rebound height, the relationship between them? Just I didn't really understand the maximum height. Yes.
Now this is the jit
Yes.
that pushes the ball. So the jit shows a linear trend. Yeah, but the rebound height doesn't show the linear trend because there is a maximum fraction of energy that is transferred from the jit to the ball.
Yes.
Not all of the energy is transferred. So
Yes.
although this shows a linear trend, the one here shows the exponential trend.
Okay. So there will still be limit on the rebound time. Yes. So reverse consider that there will be a limit on the rebound time. So that also corresponds to my opinion. So could you turn to page 21? Sorry, page 22. So could you tell me about how do you get a theory line of this figure?
Well, this is not the theory line, it's just the trend.
So it's just a trend of the rebound height. Yes, okay. So because the problem statement say that it's up to 2 liters of water. So what do you consider that if you increase the water volume will affect the rebound height? So because in your figure it just seems like there will be a boundary condition and rebound height. Sorry, I'm asking you like, so what do you consider if the water volume increase and more than 300?
Or the water level is 300 milliliters is the maximum water volume or
So my opinion is that because you use the more water volume, it would be still rebound a different rebound height. Just because you didn't try to use more water volume.
Oh, okay.
Yes.
If you use more water volume, you need to enlarge the container, like maybe enlarging the cross-sectional area, like I said. Well, like I said, yeah, like I said,
Yes.
if you want more water volume, you need to enlarge the container, like cross-sectional areas, like enlarging the radius of the container, which leads to more water surface disturbance and more energy consumption. So
Okay, I got it.
there will be more.
So, but okay, so in your jet model, I consider sorry. So you say that the radius of the container will also affect, right?
Yeah.
Okay. So in my opinion, just I said before, I consider the weight will transfer from the ground to the water and the boat. So I consider the radius will also affect. So what's your opinion about this? So because you use a jet model, and
Yeah, it will affect, but not very
Yes.
much.
Okay. So, and I asked a short question. So, do you control the ball position on the surface of water? I consider just because.
Yes.
Okay. So, okay, I got it. And could you turn to page 17 again? Yes. So, I consider that there will be a downpour, just like it will just be. Let me demonstrate it. So you consider it will just become just like a linear line here. So the boundary condition it will still increase or decrease. So because I consider you didn't use enough initial height or the rebound, I mean a different initial height. So you consider that it will be the higher, just in the higher initial height. Okay, I got it. So you just change to a page 13. So I consider that if you use like you consider the H0 is over than 170, the container will break.
Yeah.
So the break it conflicts your assumption. So
I'm sorry,
Okay.
the time is up. So please summarize your discussion in 1 minute.
okay, so I mainly asked the reporter about a fixed process between about this phenomenon. So the reporter used a jet model to demonstrate. But in my opinion, I asked the reporter if the pressure wave effect. And I also asked about a graph, is it linear or not? But I consider that in the assumption the container will break. And I also asked about how the energy transformation in the fixed process. So I consider that the energy will transfer to the water and the container. So I also asked about where the force comes from. So the reporter tried to ignore the volume force, so because they consider that it just taps the surface. we then just already sync to it. So they can ignore it. It's very little compared to the compression weight. So there's a limit value of the initial height. So that will be my summary.
Reviewer.
So I would like to ask both the opponent and the reporter that do the reporter thinks that buoyant force will be impacted in the phenomenon? Yes or no? Buoyant force, is that important?
No. I also cannot ignore.
Ignore it. Okay. And how about the relationship? Do you still indicate that it's linear to the initial height will be linear relationship to the final height? Is that correct?
No.
No. And how
Could you
about
explain your problem?
the relationship between the initial dropping height and the final height?
Oh, I got it. So I can say there will be a limit value because the content will break.
There will be boundary. And is this linear or not?
I can say it's not, but yes, in the report first is exponentially.
Okay. So well, the surface tension as the page 20. Okay. Is the surface tension between the gap that affect the motion?
Yes.
Yeah.
Okay, so yes, but the first say that you always control the position of the ball on the center of the surface the surface.
Okay. Then about the problem statement, you guys just didn't do that. What about the 2 liters optimization? What kind of parameter will cause to the 2 liters optimization of the 2000? Give me some parameters that you think about. Okay, how about the opponent?
So I can say that when the reverse try to.
Like what parameter change will cause the 2 liters
Oh, okay, I got
that
it. So I can
optimization?
say that because the compression weight, as I said before, will change. So the response time will also be different. Maybe be higher. Yes.
Okay, so it's the compression weight. Okay, and do you have any idea about the 2 liters optimization?
The radius of the curve is.
The radius of the
Yeah,
part.
radius of
Okay,
the curve.
and will there be any boundary limits that doesn't form the phenomenon?
Which phenomenon?
The ball that bounce from the water. In what conditions that it won't be formed? Okay, do you think there is any boundary limits?
Just the initial height, as I said before, it would cause the content break.
Okay, so you mean the container break and
The
okay.
contact angle. Will
The
be-
contact angle, okay. And so the last question will be, what will be the correction term if we need to apply to the real life situation? Like, is there aircraft force or something that is important in the correction term we can use in the theoretical model?
I can say that this probably will also affect, but very.
Oh, this one. Okay.
Yes.
Okay, thank you.
Please prepare for your report.
Honorable juries and fellow competitors, I'm a reviewer from Team Alpha's Qingzhen High School, and I'm going to review problem number 5, ping pong rockets. So the summary of a reporter is that in experiments they use electromagnetics to control the dropping, and you use high-speed camera to shoot the image. And the theoretical parts, they consider force analysis of the system, and the buoyant force is not included in their theory. And about different stages they have showed, and the jet's height is also calculated. And for a reporter's performance, strong points are they have clear explanation of phenomenon and have various theoretical models that is including in their investigation. And about their weak points is that they didn't focus much on the problem statement's requirements, which is 2 liters of optimized heights optimization. And the match between the theory and the experiment is not clear, and they didn't indicate about the jet's formation. And about the summary of the opposition is that in the experimental parts, they do the collisions angles discussion. Then they also have the free body diagram drawn on the board. And the theoretical parts, they consider the buoyant force discussion and also the jet's definition, like the physics concept behind it. And for their opponent performance, that strong points are they have fluence performance and they detail discuss the physics concepts behind the phenomenon, but they also didn't focusing on discussing the optimization of 2-liter water. And for the discussion, first opponent questioned the reporter about the exponential curve or not, and reporter response it is exponential. And we agree with the reporter about the form of the curve because it's about the drag force. And about the opponent asked about the water up to bigger than 300 milliliters, and the reporter responds about its boundary condition. And our opinion is that we agree with the opponents that this problem statement should be examined to higher volume of waters, and that is important. For reviewers' questions that I asked about, is there truly no buoyant force applied on it? That the reporter's response is no, and opponent is no. And our opinion is that yes, there will be consideration in the drop and the bounce, and which we agree with both of them. And for the final height relationship to the initial height, that the response is as nonlinear, and they consider it's nonlinear. And for our opinions, it's that we agree to the reporter but if it's for their model that they originally showed in their slides, that it's only energy conversion between the potential energies, that it will be linear. But if jerk is included, it's not linear according to their discussion. And also, will there be boundary conditions that its phenomenon will not be formed, that reporter or response for the angle and opinions like the break of the container, and we think that the height of water in the container is also important, which the jet's formation will be considered. And if the jet is not formed, that this phenomenon won't happen. And also the optimization of how truly the water's condition can be optimized, and reported response for radius, and the opponent says the compression wave, and our opinion is that if the jet can be formed, then it's up to the dropping heights. And that's all of my review, and thanks for your kind attention.
Okay. Concluding remark.
Well, thank you for your current suggestions, and I'm going to be talking about concluding remarks. First, dividing the process into smaller phases allows better explanation, and we did the setup that minimized the tilting angle and other factors. And the large amount of data allows us to select the suitable ones to analyze, which I have misunderstood what the opponent said earlier. We did control the angles and we did investigate various variables. Yeah, we did control the contact angle on the drop. Because we use electromagnets to release the container, ensuring it's dropped vertically, and the large database we have allows us to select the best models data. And also, one more point I want to clarify is that the reason we didn't do up to 2 liters of water is because when we need more volume of water, we need a larger radius of the cup or the depth, and when we enlarge the radius, it will result in more energy consumption, and when we enlarge the depth, it won't be practical. And room for improvements is we need to consider process done during the collision phase and experiment with higher volumes of water. Thanks for listening.
Okay. Let's take the question from the viewer.
So I have a question for the reporter. What is the main mechanism that make the ball bounce higher? I mean, what's the main force that makes the ball jump higher?
The capillary force.
Capillary force about opponent.
So I consider it will be a capillary force because that when there are more water in the container, so there will be more energy conversion at the ball. So they will cause a more energy transfer to the people.
How about the
The thing about is the jets formation, because this phenomenon is actually kind of like the water hammer effect, where the jet is formed by the cohesive force and that's impact on the ball.
what's the force behind it?
Okay. And yeah, in this part I agree with both of them about the capillary force.
Capillary force is attractive force. That means if you increase the area, or the potential energy actually goes lower. So I wonder why you can make the ball jump higher. It's not an attractive force.
Because,
Yeah.
because for larger capillary forces, it forms a deeper crater, and when it resiliences, it has more energy and it will.
It has more energy.
Yeah.
It has a more negative energy. Because it's attractive force.
To the reporter's response, that's when it's attractive more that the cavity that which forms the jets will be bigger, and the cavity determines the jet's maximum volume, and that is which leads to the bouncing height of the ball.
How about the formula?
So I can say that the ball will have a chamber at the water, so it will lead to the energy conversion at the point, so it will cause the height. Okay, so let's move on.
I have a question for the reporter. So you show a lot of the control measurements, but I don't get the important point of your whole presentation. Can you tell me which control measurement you think is more important or surprising to you, or you can show this slide.
Well, the initial height and bubbles water and also the radius of the cups are the main factors that are affecting the rebound.
Can you show can you just show your slide? So you're talking about three or four control measurements.
Yes.
I mean the data, not the conclusion. This one.
Sorry, what's your question?
No, I mean you talk about a lot of different set of measurements, different figures, but I mean there's no we can get the important information of all this data. So you mean this one is the most important data you get?
The three factors that I mentioned are all important data that affect the experiment.
The three So you mean this set of data?
No, 3 sets, and this is just one of
And
them.
what's the importance you get? Why you think it's important?
Because they affect the maximum height it gets, the ping pong ball gets. So it's really important. in my opinion.
Okay, so you think so you mean like the number, like the 500 centimeter, that's the most important result you have? Yeah.
I think you misunderstood that because in this graph it shows that the initial height is the independent variables that we're going to be investigating in this experiment. So 500 centimeters is the rebound height, and in this experiment we are investigating in the effects of changes in initial height. And there are also other factors such as the volumes of the water and the radius of the cups.
You mean this relation is the important result you get?
Yes, because and as you can see in the graph, as initial height increases, the rebound height also increases. And that's like kind of like
I thought that's sort of like expected. Like if you only talk about like the rebound height increase with initial height, I think that's sort of expected, right? So are you talking about the detailed relation or yeah?
Yeah, this graph actually we are talking about the exponential correlation of the initial height and the rebound height. And because of the air resistance and the maximum diffraction of energy that is transferred from jet to the ball, and therefore it like kind of explains why it shows an exponential correlation.
Yeah. But that's a guess. I mean, you need probably a lot more like
yes, and that's really
experimental analysis to
support
this.
the
Yeah. Okay. Thank you.
All right, so let's go on with the gradient. So let's first show the grades for the reporter. 5, 6, 6, 8, and 6. And then for the opponent, 7, 6, 7, 6, and 8. And finally for the reviewer, 6, 7, 8, 7, and 7.